what, where, all that good stuff. You guys and period 4 will have two different, slightly different exams. So anybody that's taking it online, you'll just submit it. Make sure that you submit to your class's assignment, right? Final exam period 2 versus final exam period 4, okay? And the topics that are going to be on there. Okay, implicit related rates. Now we've done at least a little bit with inflection points and concavity. We'll do one more today just to kind of practice that. And then still a couple things left over the next couple of days. So I want to at least see if we can get to the second derivative test for Extrema today. And then tomorrow will be position, velocity, and acceleration. So let's jump back in. Take out those guided notes that you got yesterday. And we'll go on the bottom of 295, did we finish f of x? That's the one where we set up kind of like our interval, stop, interval, right? Just like we did with increasing and decreasing to find mins and maxes, same thing here. We can find intervals where the graph is concave up or concave down. Cool. Let's try it with the one on the right as well. Okay. Let's see if we can find the points of inflection, if there are any. And if so, that should break the function up into concave up and concave down intervals exclusively. So what do you think? What do you think? I think I just kicked Derek out. What do you think we should do? Yeah, Chad?
We'll start by the first one. So
it is a product. Yeah, it's 2x times e to the x. I'm going to use my whole space here, but we're working on that one right there. Let's find the first derivative and see what we get. I'm going to call 2x my u, and e to the x will be my v. So u times dv. Now, this isn't related rates. We don't have to worry about like dy, dx's, and or dx, dt's, or anything like that. What's the derivative of e to the x? E to the x, good. It's our favorite. We love it. So there's dv, which actually is the same thing as v, which is kind of nice. Plus v, e to the x, du, so times 2. And let's just clean that up a little bit. 2x e to the x plus 2 e to the x. We're okay to leave it like that if you want. If we wanted to, we could factor and pull some stuff out. You can pull out 2 e to the x and just have x plus 1 left behind. Either one's okay. If we took that, set that equal to 0, and solved, and we got some x values, are those our points of inflection? If we set the first derivative equal? Now, what are those going to give us? Potential extrema, right? Could be a min, could be a max, maybe not, right? And so because it might be a list of extrema, but it might not be, do you remember what we call them just first, before we identify them as mins or maxes or not? When we set the first derivative equal to 0? Starts with a C. Critical values or critical numbers. Yeah, that'll give us our critical numbers. But that's not what we need here. We're trying to find inflection points. So we don't want to set the first derivative equal to 0. Laura?
we're going to find the second derivative.
Yeah, we're going to have to find the second derivative. So how do we do that? Here's the first derivative.
Take the first derivative.
Do it again. Good. So let's find f double prime. Now we've got a sum here, so we'll do the derivative of each separately and see what we get. Okay, so first we need to find the derivative of that right there underlined. What's the derivative of 2x e to the x?
The x plus 2.
We just did it, right? It's the same thing. So I know that the derivative of this is the whole thing because that was our original function. So I can say, okay, here comes the derivative of what's underlined in red. Sweet. Okay, plus, now, what's the derivative of 2e to the x? Well, what's the derivative of e to the x? Okay, so what's the derivative of 2e to the x? Yeah, constant. Yeah, it's just a constant. So we're good. Here's the derivative of what's underlined in green, 2e to the x. I think that's why they picked the function that they did. Because although it's a little daunting, right, seeing a product rule and exponential function, at least it's e to the x, and we don't have to worry about like ln of anything. We're all good there. Okay, let's clean it up a little bit. Anything we can simplify? Okay. This and this are like terms. What do we get when we put 2e to the x with another 2e to the x? 4 of them, yeah. Okay. There we go. All right, so there's our second derivative. There's f double prime. Okay. Now we want to find all of the x values that are potential points of inflection. So what should we do? What do you think? Yeah? Set it equal to 0. Okay. Let's see if I can sneak it in over here. 2e to the x plus 4e to the x. Oh, 2x e to the x plus 4 to the x equals 0. Okay, so there we go. If there's only one x in this equation, we just go get it, but we've got x's in different spots. One's a factor and one's an exponent. So I think, right, when that happens, when we start kind of combining different types of equations, right, we've got an algebraic one with the 2x part, we've got something transcendental, the exponential part with the e to the x, we're going to have to get those separate. So we can solve them separately. So how do you think, taking this equation set equal to 0, how could we kind of visually separate things to make it a little bit easier to solve? If we move like 4e to the x or something, move that to the other side, now I've got x's on both sides, and that's going to make it hard to solve them because now we've got something that kind of relates one to the other. I want to break them apart without necessarily moving things from one side to the other. Factor. Yeah, I like that. Good. What do you think we should factor out? 2e to the x. Sounds good. 2e to the x. So we just have x plus 2 left behind. And here it is, right? One factor with the transcendental, we'll worry about that. One factor with the regular exponential, we'll worry about that. And just like we're factoring anything, even like factoring quadratics, right? Set one of them equal to 0, set the other one equal to 0. We'll see what we get. Those should be our two answers, okay? So just so I can use some better space here, right? 2e to the x equals 0 and x plus 2 equals 0. Okay, those are kind of the two equations that I now want to worry about. Okay. 2e to the x equals 0. Well, I mean, obviously the second one's easy, right? X equals 2. Negative 2. That one's easy. We got that. So there's a possible, there should be a point of inflection. So that's where concavity is going to change. But what about the first one? 2e to the x equals 0.
Equals 0.
X equals 0? Well, so imagine dropping in 0. What's anything to the power of 0? 1, right? So that would be 2 if we plugged in 0. Divide by 2, just to make things maybe a little bit easier to look at. Still e to the x equals 0. It's kind of the answer we're trying to get if there's something we can put up there to make an exponential expression 0. some positive number, e, right, 2.7, 1828, 1828, 45, 90, 45, blah, 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 to a power equals 0. And we take a positive number, raise it to a power, and get 0. And that's okay. We're not always going to have a solution to this. This is what the empty set or the null set looks like. A little 0 with kind of a line through it. You could write it like that. You could say, this is actually kind of cool, x equals the set of nothing. It's called the empty set. That's cool too. The only answer we get is -2. It's the only one that's sure. Okay, so there should only be one spot where this graph takes a turn from being concave up to concave down, or vice versa. Again, that's probably not, I shouldn't say probably, but I'll say it anyway, probably can't happen at a minimum or a maximum. That has nothing to do with second derivative. That's a first derivative kind of thing. And so now what we can do is set up our little, right, our little setup like this, right? Well, we'll do our intervals and our inflection points. We'll check out the sign of f double prime. And that should help us with the behavior of the function itself. All right, interval stop, interval stop, interval stop. As many as you need. And since there's only one inflection point, we only need the 2 intervals around it. Thinking about the domain, yeah, I can plug in whatever x I want. There's just 2 times that. And then e to the power. I can raise e to any power that I want. So it looks like we're going to start at negative infinity. We'll end at positive infinity. Of course, stopping in between at -2. And there's our breakpoint, right? Negative infinity to -2. Stop at -2. And then from -2 to infinity. And then we just see what happens, right? And this is probably the kind of thing that I'm going to use my calculator to do this evaluating. If I don't feel like trying to do this by hand, right? Because it's got to go into here. Right? We want to put it into there and see what we get. And the thing about e to the x, that whole thing, is that it's always going to be positive. Okay, that factor, no matter what, e to some power is a positive number to a power, so they're just going to get bigger or smaller. But negative exponents just give me the reciprocal, right? So I want to approach 0, but I'm just never going to get there. So this is probably not something that I try to do without a calculator. I'm going to just jump in. I'm going to type the second derivative into y equals. Let's do it. And then plug in some numbers. Let's see. Y equals, clear out whatever you got. I had a good one in this. So 2x, where's e on your calculator, you know? There's the sound I was looking for. Make sure you know where it is. Yeah, e is the most popular basic calculus because of its derivative, right? It is the only function of x that is its own derivative and antiderivative, which is awesome. Second division, good. Second division is where that e is located. So 2x e to the x. Press the right button. Yikes. E to the x plus 4 e to the x. I want to graph it out. Let's see what this thing looks like. I'm curious. It kind of just looks like e to the x, more or less. It just looks exponential, right? It's obviously not e to the x. It dips below because of that negative x, those negative x values that could overtake it a little bit. But really all I care about is seeing what happens exactly at -2. Which is 0, so that's good. And then around it, right? Let's see what happens. I don't know. Pick a number between negative infinity and -2. -3. And I just care about the sign of that number. Now, my mode is set up to actually drop in the fraction. So I got -2 over e to the third, which just is some negative number. But in case you're using the decimal version, what was it, -3? Is that what we said? Negative something. That's all I care about. I just care that it's negative. It's -2 over e to the third, but all I really care about is the sign. So if the second derivative is negative, what is the behavior of the function in that entire interval? Got to be concave down. Okay, the whole part of this, we are concave down. Okay, when x equals -2, when we have f double prime to be 0, what do we call that value? Inflection point, good. Inflection. Okay, and then something between -2 and infinity. Pick any number in there. -1 sounds good. 0, 1, 2, 3, anything you want. I'll drop -1 in because that's pretty close. And I get something positive, 0.735, blah, blah, blah. I don't care what size it is, I just care that it's positive. So behavior of the function at that point? Okay. Okay, so that's the idea. That's kind of the basics of using the second derivative to break this graph into certain pieces and see what's going on. I don't know, let's check it out. 2x e to the x, right, was the original function. Okay, at -2, right there, this spot is where we have a concave down section. Kind of hard to see it being super concave down, but it is. And then concave up. Okay. Now, do we have a min or a max at -2? No, definitely not. But let me ask you this. Look at that green section there that we are guaranteeing, right, by just checking that second derivative, it's definitely going to be concave up. What do you see in that green section that exists that would be an important kind of calculus point that we might want to find along the way? There is a relative minimum, absolutely. Okay? And think about this. If it is concave up in a section, can there be a relative max in that green graph that I just drew? No. On this blue section, concave down. Can there be a relative minimum if it's concave down? No. And that, for me, is actually probably the biggest takeaway for the second derivative, is that realization right there. That if we are concave up, there cannot be a maximum. There could be a minimum. Right? Good. Now, we have maybe just part of the section, maybe we only have like this part that's concave up. And then there's an inflection point, and then all of a sudden we're concave down. So, maybe there's a minimum, maybe there's a maximum, depending on what side we're on. But I can guarantee for sure that if it's concave up, there cannot be a maximum. There could be a minimum. Right? Same thing with concave down. There can't be a minimum, but there could be a maximum. And so if we can maybe use some ideas like this and start putting some like first derivative and second derivative ideas together, maybe there's a way for us to find relative extrema without having to find critical numbers and then test on either side. Let's see if we can figure out a way to test for relative extrema using the first and second derivative. Okay, and that's kind of what's next. And I think, as nice as working through this problem will be as we prep for prep for the final. I kind of want to save some to give you some to practice. Okay. The thing I want you to notice about this question on the top of page 296, right? 295. Here's f of x. Here's f of x. Find inflection points. Look what they gave us. They already gave us the derivative. So we don't have to do it twice. We just have to do it once. Okay. So they might start us at the function, or they might start us at the derivative. So we have 2 derivatives to do, or 1, kind of depending on what they're looking at. Okay, but I want to look at the bottom of this page. We have a first derivative test, which is find the critical values, and then test on either side to see does it go increasing to decreasing, so it's a max. Does it go decreasing to increasing, so it's a min, or do we not see a change in sign, so we know it's neither? Right? There's I think, a nicer version of ways to find relative extrema, and it's called the second derivative test. Okay. And here's the process. Okay. First, we're given a function, right? They're giving us some f of x. Okay. So given f of x, if we want to try to find possible relative extrema, what do we know should be true at a min or a max from a kind of a calculus perspective? So they give us some function, it's polynomial or trig or exponent, whatever. And we want to try to find a relative extrema. What do we have to do first in order to start narrowing our choices down for x values that could produce a min or a max? Like, what is that possible list of numbers that could be a relative min or a relative max? All of our critical numbers. Okay. How do we find critical numbers? What is that process? Yeah.
You find the derivative, and then you start looking 0 on itself.
Good. Okay. So there's no way to find relative extrema without at least finding the critical numbers, right? Finding where the first derivative is 0. Now, don't forget, functions can be defined at points, but maybe the derivative isn't, and it still could be a min or a max. So sure, maybe the derivative is equal to 0 and we can solve. Where else might we find a min or a max at a spot where the function is defined but the derivative is? What image in your mind might you remember from yesterday? Where a graph has a minimum or a maximum, but it's not at like a smooth, nice, rounded turn where it's a min or max. A cusp. Okay? So that spot where f of x is undefined is something that we do not want to forget about, right? That's going to be at our cusp. Now, how often does that happen? Rarely, right? That's your powers of like 2/3. Okay? So 2/3, 4/3, 5/3. Okay. Cool. Now, here's what we can do. If we, let's stick with blue. If we find the second derivative, so that we have that function that kind of tells us about concavity, right? Plug in a number. If you get 0, it's an inflection point. If you get something positive, it's concave up. If you get something positive, negative, it's concave down. Now that we have this list of critical numbers, maybe there's 1 or 2 or 3 or 10 of them, whatever, here's what we can do, okay? We find the second derivative. And we can test all of our critical numbers. I'm just going to put C on, okay? All of our critical numbers in the second derivative. And there's really only 3 possibilities once we plug a number in. Okay? We either get 0 again, right? Find a critical value, sweet. First derivative is 0 or it's undefined, awesome. I plug it into the second derivative and I get 0 again. If you get 0 again, plug in a number into the second derivative and it gives you 0, then what is that number? What does that value represent? It's an inflection point, and it is not a min or a max. It's an inflection point. And that's not part of our list, right? We're trying to find mins and maxes. Okay? It is not a min or a max if the second derivative pops out with a 0. Right? That's that like cubic turning point. Okay? Where concavity changes, but it's not a min or a max. Now, what if the second derivative is positive at that point? And so we're at a critical number, and the second derivative is positive. Well, tell me what you know about the shape of a graph when the second derivative is positive. It's concave up. So concave up, I got this whole section that looks like this. But I picked a point where the first derivative is 0 or undefined. And I'm somewhere in this shape right here. What is that point if the first derivative is 0 and the second derivative is positive? It's got to be a minimum. Okay, then x is a relative minimum. Has to be. There's just no 2 ways about it, which is so nice. I can count on that. And I don't have to worry about really checking on either side. I just find a critical value, plug it into the second derivative, and I see what I get. Okay. Same scenario. Find a critical number, you plug it in, and you get something negative from the second derivative. What is the shape of the graph if the second derivative is negative? Okay, down. So this whole section here, some point in here, but the first derivative is 0. What does that point have to be? Has to be a max. And that's the second derivative test. Find the first derivative, get your critical numbers. And with every single one of those numbers, plug them into the second derivative and see what happens. You get 0, not a min or a max, it's just an inflection. You get a positive value, x is a min. You get a negative value, x has to be a max. And honestly, this is the way that I would find mins and maxes if the derivative process isn't all that difficult. Sometimes defining the first derivative is hard enough and you don't want to do it again, because maybe the first derivative is more complicated than the function, which makes finding the derivative again just a whole lot of work. So it's kind of up to you. Usually they don't say, hey, use the first derivative test to find mins and maxes, or use the second derivative. They just say, find all of your relative extrema, period, end of sentence. Do it however you want. Pick whichever way you like best. You want to do a first derivative test with interval stop, and you just check first derivative? Awesome. If it's easy enough to find the first derivative and the second derivative, usually that's the fastest way, as long as your derivative skills are pretty good. Okay, so go ahead, turn the page. Let's try this thing out for a couple. Use the second derivative test to locate and classify. So find them and decide min or max. for all x values of relative extrema for each function. Okay, what should we do first? Calculate, find the derivative. Sounds good. And it's nice, easy polynomial, so we like that. F prime 4x to the third minus 12x squared. So that's F prime. Okay. What do we do with that? Set it equal to 0. 4x cubed minus 12x squared equals. Because I don't want to jump into the second derivative just yet. I got to find my critical numbers first, because those are the spots where I might have a min or a max, kind of depending on what we got. Okay, 2 different powers of x. Got to solve it.
Factor out 4x squared.
Sounds good. Factor out that 4x squared. What do we have left? X minus 3. Cool. So as fast or slow as you want here. What are our critical numbers? 0 and 3. Okay. So here's our set of critical numbers, 0 and 3. So 2 possible spots for relative extrema. Now, maybe they are, or maybe not. I don't know. But these are the only 2 possibilities. Okay, now what? How are we going to test to see if 0 is a min, a max, or neither? And if 3 is a min, a max, or neither? Plug it into what? The second derivative. Do we have the second derivative yet? So let's find it. Let's find f double prime and see what we get. How do we find the second derivative? Take the derivative of the first derivative. 12x squared minus 24x. Now, do we need to set that equal to 0 and solve for anything? No, that would just give us inflection points. That would give us a spot where concavity changes, and that's not the question. Sometimes it is, right? Sometimes it says, here's a function. Find your inflection points and, figure out your intervals of increasing, decreasing. Great. Take the second derivative, set equal to 0. No. What I want to do now to figure out what's happening here is to do f double prime of 0, see what I get, and f double prime of 3, see what I get. And that will give us min or max or neither, depending on what we've got. Show the substitution if you think you need to, or just plug it in, see what you get. Plug in 0, what do you get? 0. Is that a min? Is it a max? What is it? Inflection point. So that should be a spot where we go from concave up to concave down, or vice versa, which is not going to be at a min or a max. Plug in 3. Again, really all I care about is the size of the number, positive versus negative. But hey, let's just figure out what we got. 9, 108, 108 minus 72, what is that, 36? So that's positive. If your critical value exists in a space that is concave up, right? This is the picture that I'm looking at in this moment. Right there, right? That's going to be our spot, okay? That is A. And I never had to go in, do interval stop, interval stop, interval stop, and plug numbers in all over the place just to get values. Find critical numbers, plug them into the second derivative. Life is good. I like it. I like the second derivative. That's way more than the first derivative. I feel like it's like fancier and neater, faster if you can find derivatives quickly and plug them in, especially if you have a calculator and you can just drop numbers in. They work out real nice. And that's the second derivative test. And so when I said this about a half hour ago, and I said, okay, what's going to be on this? Implicit related rates, inflection points, and concavity, and the second derivative test for extrema. There. That's all it is. Okay? I'm going to give you a function. I'm going to say, I'll probably lay it out pretty clearly. Find your critical numbers. Test whether or not they are mins or maxes. And I'm just going to leave it like that. You want to do first derivative test? Awesome. That's a chapter 3 thing. You can do it. Chapter 4 will allow you now to do a second derivative test. Yay. Okay, cool. Let's do one more. Let's do the trig one. Why not? We haven't seen trig in a little bit. Let's do the same thing. Same idea. Now, you want to be careful. Sometimes they give you the derivative. We only have to set that equal to 0. Here they give us the function, so we're going to have to find our values at work. They're keeping us just within one rotation of the unit circle, so we don't have to find too many answers. What should we do? Derivative. All right, so it's the derivative of a sum or difference. So we'll just find each individual derivative, and we'll see what we get. The derivative of cosine. What's the derivative of cosine? Negative sine. Okay, so what's the derivative of 2 cosine? Negative 2 cosine. Or negative 2 sine. Yeah, negative 2 sine theta. And then theta. What's the derivative of theta? So this is the derivative of negative theta, so negative 1. Okay. There's our first derivative. What should we do with it? Set it equal to 0. We're trying to find critical numbers first. I need that list of possibilities where there could be a min or a max. And so the only way to do that, here in Calc A, is to set that first derivative equal to 0. Solve. Now we're solving for something with trig. So we're going to have to isolate that trig function and then figure out where on the unit circle it's going to be true. And that they're always going to give us unit circle spots, certainly early on. Maybe Calc B, C, maybe they'll challenge us a little bit. But here, hopefully, it's a spot where we can find an answer that works. Add 1, divide by negative 2. Sine of theta equals negative 1/2. Somewhere between 0 and 2 pi is at least one value of theta where the sine of that is negative 1. I hope you start picturing the unit circle. Kind of almost closing your eyes and seeing if you can find the spot where that's true. Are we looking for the x value of the coordinate or the y? Y values. Sine, y. Where is sine negative? Third and fourth quadrant. So looking for answers between pi and 2 pi, where the y value is negative 1/2.
5 or 6 and
11 pi.
Not 5 pi over 6. That's still second quadrant.
11.
We want 11 pi over 6 and 7 pi over 6. 7 pi over 6, because that's 210, and then 11 pi over 6. There's our 330. If you use the calculator and you did inverse sine of negative 1/2 and you're in degrees, it is going to give you negative 30 as your answer, right? Because it's going to open up the angles in both directions. It's going to hit 11 pi over 6 first, and because it hit in the negative direction first, it's going to give you the negative answer. That is your reference angle. If you know what quadrant you're in, just use that as your reference. Okay? Oh, I got to be in the third and fourth quadrant because sine is negative, so I have to be 30 degrees below the x-axis. Sweet. All right, so there are our possible critical numbers. Well, there's our critical numbers, our possible extrema. We don't know until we try them out. Where are those two values going to go? Into the second derivative, so we got to do that first. We have to take the derivative again. What's the derivative of sine? Cosine. So what's the derivative of negative 2 sine? Negative 2 cosine. What's the derivative of negative 1? 0. So there's our second derivative. And what we want to do is drop in those two numbers. 7 pi over 6 and 11 pi over 6. And let's see what we get. Calculator for sure if you want, or you can just kind of think it through. Because all I care about is 0 or positive or negative. It doesn't really matter how big it is as long as I know where we're at. Let's just try it without the calculator. Careful, radians versus degrees, what you're typing in versus what you want to get back. When I do inverse, I'm always in degrees so I can recognize the answer. When I'm just plugging it in and seeing what I get, if it's in radians, I'll be in radians. If they give it to me in degrees, I'll do it in degrees. All right, so cosine of theta at 7 pi over 6. Really, all we care about is positive or negative. Is cosine positive or negative at 7 pi over 6? It's negative. So what's negative 2 times that negative number? Something positive. I don't care what it is. Now, sure, it's this, right? Negative 2 times radical 3 over 2. Negative radical 3 over 2. So that's the square root of 3. But all I really cared about was that this was positive. Because if the value of the second derivative is positive at a critical number, the shape of the graph is concave up. And if the graph is concave up, what type of value does this guarantee? Got to be a minimum. And it's weird because you see like positive, but I get a super low number because it's a minimum, right? But that's just the shape. Okay. Cosine of 11 pi over 6. The x value on the unit circle at 11 pi over 6. Positive. We're in the fourth quadrant. Now, exactly, it's radical 3 over 2. But all I really cared about was that that number inside is positive. Okay. So what's negative 2 times a positive number? It's something negative. Now, what is it exactly? Well, it's this, right? Negative radical 3. All I really cared about was that this was negative. If the second derivative is negative, what is the shape of the graph? Concave down. If it's concave down at a critical number, what is it? Got to be max. Yay, second derivative test. Done. Okay. There you go. Second to last topic. I do have 7 minutes, so I am going to start tomorrow's stuff because tomorrow's a little shorter day. But this last idea is not in here. Okay? The rest of this is just second derivative practice. Okay? Can you find your inflection points? Can you find your relative extremity using the second derivative test? Okay? So the thing that I want to show you is something outside of the guided notes that I think is just interesting and fun and kind of a nice application of calculus. So I'm going to ask you temporarily, just for the rest of today, to put those guided notes away. You don't need them. We can come back to them on Monday, Tuesday. But starting this today should give us a chance to finish it tomorrow. I'm going to keep it super straightforward. I just want you to see it for the first time. If you have taken or are taking physics, this won't be brand new to you. The calculus side of it will be, but the actual equation for what we're about to do is not, which is nice. Okay, so I'm just going to jump onto kind of the whiteboard here. And so jump into your notes so you can write a couple quick things down for our last idea in calculus. That's so sad. I just want to keep teaching you guys. You guys want to hang out like just all summer? And keep going? I would, man. I really would. I would come here and just hang out with you guys. There's so much more. Oh my goodness, so much more. And lots we didn't get to. That's okay. But we will finish chapter 4, which is awesome. We just did it. You just finished chapter 4. I'm just adding to it. So we actually did more. Okay. So here's our last idea. It's, and I could say this in a lot of different ways. I don't know. I could say it so many ways. I'm going to call it the calculus of physics. Meaning let's watch what happens when like something physical actually moves through space, right? Let's chuck something through the air and watch it change. Let's watch a car speed up. Let's watch a person jump off a diving board. Let's whatever, right? Let's actually watch. Let's watch gravity happen. Let's watch gravity take over. And so this is the physics of objects on Earth. Okay, so we're only going to use gravity. And welcome to high school and undergraduate level physics, where we always neglect almost everything. Because there's so much about physics that is way too complicated to simplify enough to do the calculus with. We are going to ignore friction. We're going to ignore air resistance. We're going to ignore rotational velocity in 3 dimensions, okay? We are just going to do 2-dimensional physics. We're objects in 3 dimensions. And that's going to make our lives a whole lot easier, okay? You're going to hear that anytime you take physics. Let's ignore friction. What? What do you mean ignore friction? That's not a thing, right? You can't just ignore friction. That's like everything within the life that you lead has friction. Even air resistance is basically friction against the air, right? Have you ever seen the video? Maybe we'll watch this. Ever seen the video of them dropping a hammer and a feather on the moon? Oh my God, you seen that? Oh, maybe we'll watch that. It's so like in like the 60s and 70s. They like bring this like super old, like they go to the moon, they bring a hammer and a feather, and it's so crazy. Because think about it, like drop a hammer and a feather right here from 5 feet up. What's gonna hit the ground first? The hammer. Why? Air resistance on the feather. That's why birds can fly. It's because of so much air resistance on their feathers. A lot of surface area. Maybe I'll show it to you. Supplement to that, and then I'll give you one thing, and then we'll get out of here. Same video, but redone much later, like not all that long ago, maybe 5 or 10 years ago, where they take, I think it was still feathers and like a bowling ball, and they drop those. You see that?
Isn't that one in like a vacuum?
In this huge vacuum, right? This like 300-foot tall. Oh, so cool. All right, cool. So here's what I want to give you, just the basics, okay? There is a formula that we can use to track position of an object acted upon by only 2 forces, gravity and any initial velocity that we give, okay? The difference between dropping a hammer and throwing the hammer into the ground, or throwing the hammer straight up, okay? We could also throw the hammer straight out, and of course that's going to affect it a little bit differently, okay? What we have is what's called the position function that tracks an object's position acted upon by only 2 forces, gravity and initial velocity, okay? They call it S of t, okay? It actually comes from the German word Strecke, okay, because it was a German mathematician that kind of did this. Strecke means path, or really street, but path, okay? Here it is. 1/2 g t squared, okay, where g is the gravitational constant. The force of gravity acting on an object at any point. Okay, and I'll give that to you tomorrow. Plus v sub 0 t, where this is any initial velocity. Right? So did I throw it down into the ground? Did I throw it up into the air? Did I throw it out? Okay. Plus s sub 0, any initial height above the ground. Okay. So did I throw it from 5 feet? Did I throw it from 20 feet? Did I throw it from 0 feet, right? Did I kick the soccer ball up off the ground? Okay. If we have that, we can do something with it, and that'll be tomorrow. Okay. Thanks, everybody. I will see you tomorrow. Remember, late start Friday. Late start Friday mañana.
Thank you.
Thanks, everybody. Have a good one. Hi, Rach.
Hello.
How are you feeling? Any better? Okay, good.
It's about like a 9 to 3. What better?
Okay, good. So you saw a little bit about what we did today with this whole second derivative idea. But it might just be worthwhile like watching the video for the last couple of days and just kind of seeing what the second derivative does for us in terms of, because you know how like first derivative told us about increasing
Yeah.
versus decreasing? Second derivative tells us about concave up versus concave down. That's the only difference. It kind of gives us like, it breaks the function into sections. Just like first derivative with the whole increasing decreasing thing. Now we can break it into sections that are concave down, where it kind of opens like a parabola down, or concave up. And polynomials are really nice because they're always kind of in those like smooth and rounded sections. Some things aren't, but a lot of what we study just first time through with Calculus A is the easiest version of all that kind of stuff. So yeah, maybe just watch the video. The packet that I gave you today is what they got on Monday.
Okay.
So you're only a couple of days worth of things to watch. So
And then I'm not going to be here tomorrow because
Okay.
I have an AP test.
okay, so tomorrow, all we're gonna do is we're gonna take this function and we're gonna say, okay, first, what's the gravitational constant? Well, there's the metric system in meters per second and the imperial system in feet per second. So there's two different ones. Have you taken physics
I'm
at all?
taking it next year.
Okay, so you might not know these numbers, but they're constants, so which is really nice. It's negative 9.8 meters per second squared, or negative 32, no period there, 0.0 feet per second squared. It is an acceleration. It's a gravitational acceleration of an object, because imagine like dropping something from 100 feet, it's going to speed up as it goes, right? Because gravity is going to keep pulling and keep pulling and keep pulling, so it's going to go faster and faster and faster. And so eventually what's going to happen is we're not even going to leave it like this. I'm just going to call it like negative 4.9 t squared or negative 16 t squared right away. I just wanted people to see that because sometimes they give us in meters and sometimes they give us in feet. But if this is an object moving through the air, we can figure out how fast it's moving by finding its rate of change. Velocity is the derivative of position. Acceleration, how fast your velocity is changing, is the second derivative. That's what we're going to do. I'm going to give us a function. I'm going to give us some initial. I'm going to say, I throw a ball up at 50 feet per second from a height of 10 feet. When does it hit the ground? How fast is it moving? When does it hit its highest point? We can use this equation by just like plugging in whichever g we need, dropping whatever initial velocity is given, and sometimes it's 0, right? I let go of the hammer versus throwing the hammer down. It's gonna make a big difference. And then any initial height. So we'll do that for at least Friday, maybe a little bit on Monday, just to kind of practice with it. But that's it.
All right.
Good luck tomorrow. And let me know if you need anything. I'm happy to help. Of course. Where are you going?
Athletic training.
Okay.